from University of Wisconsin-Madison. He's a professor of mechanical engineering. He's been faculty there for 20 years, right? Since 2005. And he's one of the technical leads of Project Chrono, which is an open source multi-physics simulation framework. And he'll be speaking about the body and mind design in robotics and how to use digital twinning in support of designing and building robotic systems, including for space. Each speaker has 15 minutes. Dan, take it away.
Good. So I set the clock to 14 minutes. I like to talk, so I need to make sure that this alarm sets off because otherwise I keep going on and on and on. Okay, so my name is Dan Negrut. I'm with the University of Wisconsin-Madison, and I have to say that these days I'm somewhere like halfway. You know, there are people who are thinking and people who are doing, and right there in the middle is a sweet spot. People who are talking, I'm there. Just talk. These are the people who do and think by and large. Okay, so this is an undergrad. It's a bunch of graduate students from the most senior here to the least senior here. These are non-students. I'm one of them. So are other three people. And there are some collaborators, mostly from Italy, because that's where people, like our partners, are in Italy. So I have 15 minutes, and I cannot tell you basically how things are done in our lab, but I'm going to tell you a little bit about what things are done, okay? And if there is interest, we can talk more later. So our interest is in simulating something like this. This is a snapshot. This is associated with the Artemis mission. There are like 3 groups of companies competing, like bidding for like this vehicle to move astronauts around. This is one team. This is another team. I was part of a different team yet, but I'm interested in simulating something like this, and I'm particularly interested in this and the terrain and the deformation of the terrain and such. So how do we do that? As Lutz alluded to, we develop software. It's called Chrono. It's open source. It's distributed, basically unfettered use distribution under BSD3 license. It's multi-physics. And some information here is been around for about 27 years, of which 18 years I was part of the development effort. And it has like a C++ backend, but it has like Python bindings. And just here, to put things in perspective, it has been downloaded about 146,000 times, the Python version of Chrono. Chrono C++, as I said, is older than this is for the last 4 years. So I'm going to step back a little bit and start talking about experiments, because that's what we conduct in Chrono. An experiment, if you go to the dictionary and look, it says like, you know, it's a procedure. Basically, it's something to carry out under controlled conditions, and you do so to test a hypothesis or to discover something. So this is what people are saying. It's not my, invention, but that's basically, it fits very well what we're doing with our software, actually. So in the lab, we think about experiments like this. So we have like level 0 experiments. These are like basically real world. Then we have like level 1 experiments, which basically is kind of like the digital twin of the world. And we have like level 2 experiments. And I'm going to talk for like 2 minutes about this. So here's an example. This is a level 0 experiment. It's an actual thing. And you dig with it and you see how it digs. This is the Chrono counterpart. And this is like the level 1 digital twin of the level 0 experiment. But just think about it. Like in the simulator, I do the same thing. I have a hypothesis. I want to test something. I want to discover something. I want to ask, like, is this design better than the other design? And I just basically carry out an experiment. Now, the level 0 experiment unfolds according to the laws of physics. The level 1 experiment in Chrono, I have models, and they make an attempt to capture what happens in the real world. So basically, it unfolds following the laws of those capturing those models, okay? And then in ideal world, the level 1 would be like the digital twin, a really good replica of what happens in the level 0 experiment. So level 2 experiments, these are like super fast experiments that are needed in our world, both for level 0 and level 1 experiments. And just to put things in perspective, these are very fast, and this slide explains what they are. For instance, if you have a vehicle that does Model Predictive Control, MPC, it needs a model. If you do estimation, you need the model. You need sometimes to run these models super, super fast, like thousands of times faster than real time, so that you can figure out online what to do. So these level 2 experiments are sometimes carried out within the context of L0 experiment. You have a vehicle. Or in Chrono, we have a simulation, level 1 experiment, and then inside that simulation, you have another simulation. Okay, so that's basically the level 2 experiment. And another way to look at it is like this. You have like the actual thing. This is a level 1 experiment, like a replica of this. Maybe you want to do human in the loop, like lesser fidelity, and then you have something that is like roughly a good model of the actual thing. So we use Chrono for integrated mind and body design or wellness. This sounds like yoga and like something, but it's not like that. So we do it to design the body of the vehicle. We do it to design the mind of the vehicle, and there is an interplay between the two of them. And I'm going to explain what the body is and what the mind is. I told you that the lab was part for 1 year of this project for the Artemis mission, trying to compete with other teams. But we had to simulate something like this. And the hard part is this. It's a deformable wheel. And this is basically part of the body. And the question is like, is it going to carry the day? Is it going to collapse and so on? So these are some simulations that we did. And as far as I know, I haven't seen this happening. Like you have a finite element deformable wheel working on deformable terrain. This is one set of partial differential equations. This is another set of partial differential equations. This is governed by one set of physics laws, and this is different physics. And this is like basically the shell elements that we use in the vehicle. Now let's talk about the mind. What do I mean by that? So on an actual robot, you have sensors like camera, LiDAR, and so on. And then you have like an autonomy stack that takes inputs from these sensors. And there, I have all sorts of processes like perception and planning and control and such. And a command comes out and it goes to an actual vehicle, and it's an agent. That agent interacts with the environment. It digs into it, or it bulldozes it, or it sinks into it, and so on. So there's this interplay, and basically this is where the body is, but this is where the mind is. And what we do in simulation, we want to eliminate the actual sensors and the actual agent or vehicle, and we simulate these. But what we want is to keep the same autonomy stack running on the same hardware in the loop. And another way to look at it, and this is, I don't have a rover in my lab, we have like, scale vehicles, but this is the actual thing. This is the digital twin of this guy. And then you have like the actual processor, which in this case is an NVIDIA Jetson, and it runs an autonomy stack. And basically there's like a ROS ecosystem, and this thing is oblivious to what sensor feeds come into it. And then a command goes out, but this thing here, the mind, and the hardware running the software doesn't know if it goes to a digital twin of the actual vehicle or to the actual vehicle. So that's what we want to basically assess. You want to help design the software and test the hardware in the loop. So for this vision, like designing, using experiments to design the mind and the body, to that end, we have to simulate simultaneously a couple of things. So the sensing needs to be simulated, the agent dynamics needs to be simulated, and the environments. I'm going to go super quickly through all three. So first, environment. What do I mean by that? So take a look at this wheel here. Right? Oh, this is like a rear wheel drive vehicle, and it tries to push basically, through like a pile of terrain. This process, it's important. This is the environment for us. This is the agent, but I'm interested for now in this terra mechanics problem. Here's another example, like, this like some vehicle, like rovers is like Viper. Obviously it doesn't have like a blade, but for the sake of like making a point, this is Earth gravity, this is moon gravity, and you look at, okay, what are the differences? We actually put a paper out on this very issue recently. So when it comes to terra mechanics, in Chrono, we have like various levels of fidelity. We have like a rigid terrain model, soil contact model, which is Becker, Wong, Gianossi, Hanamoto, old school. We have what is called a physics-based continuous representation model, and we have like DM. And this is fidelity versus cost, simulation cost. So DM is high fidelity, but also high cost. This CRM is something that it's emerging, and we implemented it in Chrono. and it comes close to real time at a high level of fidelity. So, okay, what does it take to implement something like this? So because it's physics-based, you have like the balance of mass, balance of momentum, and then you have a law because you don't have a hyperelastic material. It tells you how the terrain changes. It's a hypoelastic material, hypoelastoplastic material, and basically these are the equations that tell you how the soil deforms. Now, in terms of performance, I want to make sure that I highlight this thing. I wrote kilometers. So we can have simulations of terrains that run for anywhere from 5 kilometers to 29 kilometers. So we have like active domains. We load everything in memory. In this case, we use some like H100 GPUs from NVIDIA. And basically this also shows you how the solution scales. For all purposes, linear. This is terrain length. It's a log scale. It goes to tens of kilometers. And the real-time factor, how much slower than real time, this is real time. So it's like 2 to 3 times slower than real time, and it goes from there. But it's fast and it's vast. So that's a good thing. Now, agent simulation, this has to do with like, now I'm focusing on this fellow, not the terrain that it moves on. And it has a suspension, it has tires, it has, probably like electric motor and so on. So how do we simulate that? So there are some other equations that need to be solved. They are discretized to lead to a set of complementary, like differential variation inequalities. They are solved numerically in conjunction with terrain, and you get the simulation of the entire system. Last thing, sensor simulation. So you need to generate synthetic data for GPS, encoder, IMU, and so on. So just for the camera, we have like a physics-based model, and they're like basically data-driven models, but that's a different story for a different day. You have like meshes, material properties, textures, and you have like a camera model with like lens, and then you have like an image sensor, you have image signal processor artifacts, and at the end you generate a PNG that comes out, let's say at like 20 frames per second or something like that. It's a synthetic image that goes to the perception stack. So when it comes to like the camera, there are like various ways for the light transport. If you go to the moon, then the light transport doesn't happen as on Earth because there's no dispersion, the scattering is different. So here, this is an actual thing from NASA Ames. Uland, probably back in the day, generated this. There's the polar data set, and then we generated synthetic images in the image of that. There's a paper about this as well. So this is another example, and just to put things in perspective, what I said is that at the end of the day, to implement this vision about designing the body and the mind simulation, you need sensor simulation combined with agent simulation combined with environment simulation. So there are like a bunch of modules in Chrono that kind of like come together to make this vision a reality. I'm going to skip them, but I just want to end on this slide because I don't want to project this image that Chrono is like the best thing since sliced bread and is like the silver bullet. So as I said here, it's a research code and it has rough edges. It's not like Microsoft Word. You open it and you start typing. It has like a steep learning curve. That's the way it is. And I just want to be honest about it. So it takes a certain amount of effort to set up an L1 experiment, which is a good replica of a level 0 experiment. However, if you take the time to do so, at that point you can scale up because you can go to cloud computing, or probably if you have small simulations, you can run many of them on the GPU, and then you can do RL, or you can do Bayesian optimization, or you can do calibration and so on. And I have this picture here just to show, this is like here, it says Wisconsin on this rover, just to make the point that it's not a toy and it's not something that like me and like 15 other enthusiastic people develop for no good purpose. So with that, I want to thank you for the opportunity, and I probably have like 1 minute to take any quick questions.
Yeah,
I think
because
20 seconds.
that's a great idea, because we can, I guess, do one quick question, and then later on we'll have a panel, like was the same format as yesterday, and we can have more interaction with the audience. Yeah,
Thanks.
please stand. Perfect. 9.
Yes, 4 seconds left.
Time.
Okay.
Quick question while we're changing speakers.
Sure, over here.
Go ahead.
Yes.
So when you're doing the terra mechanics simulation with the wave insert, have you also tried applying real world texture to apply real world textures on top of that. So not only is the physics real, but it also looks real.
Yes, yes. It's coupled with the sensing. So we, based on the tram mechanics model involved, we bring different mechanisms to render images based on the deformation terrain. So the answer is yes.
That you've gotten that to run real time.
Yeah,
Really?
you can come up with a texture offline, and then you just apply it at runtime. There's not a bottleneck. Solving the partial differential equations, we have like millions of degrees of freedom. That's where the hard part is. Now, real time, I do not have a good reason to do real time unless I have human in the loop. Even if I have like a controller in the loop, I can throttle things up and down to test the controller. The only time when I need real time is when I have a human loop. If I can, I want to do better than real time. So real time is not, to me, unless there's a human in the loop, then that's a different story. But if you want to test a controller, if you want to test many other things, you don't need real time. If you do RL, you want hundreds of times faster than real time, if possible.
So what kind of hardware do you need to scale that? Like I've got 18 wheels and I'm doing so next generation.
So we do we have the camera model implemented on NVIDIA GPU. So we use, have you heard of optics?
Yeah.
Yeah, we use optics for ray tracing and such.
Maybe to add a comment to the real time part, by the way, I really enjoy your topic. Really wonderful work. For real time, for example, the tire would have the interaction with the land.
Yes.
Right? And then it may create a tire mark. Actually, from the perception localization point of view, you can utilize that tire mark for your perception.
You estimate split or
Actually, one example for real time simulation.
But if I picked it up, okay, how about I let you?
Yeah, we're just about ready, so
Good.
we can continue that during the panel portion. But thanks a lot, Dan. Yeah.